All right, the last day of easy physics time. So let's do some legit problems, like this one. A large boat, like the one shown above, has a mass B and can displace a maximum volume of VB. The boat is floating in the river with density of rho water and is being loaded with steel beams, each of density P, rho steel and volume V steel. The boat owners want to be able to carry as many beams as possible. Sounds reasonable. Derive an expression for the maximum number n of steel beams that can be loaded onto a boat without exceeding the maximum displaced volume in terms of the given quantities and the physical constants as appropriate. All right, so let's think about what's going on here. So we know the formula for this. We know that the force of gravity is going to be pulling it down and the force of buoyancy is going to be pushing it up. But those two things have to be equal. So let's calculate the force of buoyancy. The force of buoyancy is rho Vg. All right, and that has to equal mg of the boat plus nmg for the steel beams, because times however many there are. Now we want to solve this for the n, and we're going to put in the real values here as well. So let's solve it for n first. Let's plug in the real ones first, then we'll solve it. So we're going to have rho water, that's what they call it, right? Times V, what's the volume of this one? This is the volume of the boat, so that's going to be VB times G. Well, we can cancel out G's from everything, which will be nice. All right, and then we're going to subtract M. What's M is this? This is MB, mass of the boat, and that's going to equal N. Well, but we don't have mass of the steel, we just have the density and the volume of them. So we're going to replace that with rho V. So rho steel V steel. Just like we did, just like the water side of the equation, basically. So to solve for n, we just got to divide. So n is going to equal rho water V boat minus M boat divided by rho steel times volume steel. All right, and that's it. So that's how many steel beams you can load on there. Hey, for part B, Captain realizes that oil is leaking from the boat. That's not good. Creating a thin film of oil on the water's surface. In one area of the oil film, it looks mostly green. Explain in detail how constructive interference contributes to the green appearance. Assume the index of refraction for the oil is greater than the index of refraction. All right, so let's write that down. So N oil is greater than N water. Okay, so what's going on here? Let's draw a picture so we can help explain it. We don't need the boat really anymore for here. So this is the surface of the water. I'll call it H2O. And then we'll have some oil on the top. We'll use the yellow. We'll see if that shows up. Barely. All right, anyways, there's the oil. I'm going to switch to this. Okay. So what is happening here? So when the captain is looking down at the light, there's a couple things that can happen. We did a problem that's kind of like this. For light, I'm going to use this light green color because I can still see it. So we've got this ray coming from the sun. So what it's going to do is it's going to reflect off in part. So there's going to be some reflection there. And it's also going to refract into the oil. All right, so there's some refraction going to happen right about there, we'll say. Now, we know that the water has a lower index of refraction than the water does. The oil has than the oil does. The water has the lower one. So it's going to go something like this. It's going to be less perpendicular, right? The higher the index, the more perpendicular it's going to be. But what will happen is it won't all reflect off of the oil or refract into the water, so it'll bounce off. So it'll do something like this, and then, at the same instant, and then it will be going this way. So what is happening is these two waves right here are having constructive interference. Now, because each color has a slightly different index of refraction, never mind, that doesn't matter. But what does matter is that you have this amount downtime, all right? This guy right here. So let's pretend like just this light, let's pretend for a moment here that this ray right here, the black one, departs at the same time as the red one, okay? Now, this one has the black one has a head start, but what we know is this guy has to equal some multiple of the green wavelength. All right, because that way they can have constructive mirrors. Let's just say it's one wavelength. So this guy is going to do there, and then it's going to match up with the black wavelength. That's how the green color can get prominence. All right, so what would you write? You would show you'd show a picture like this, show how the difference, the path difference, is going to be a multiple of the green wavelength as opposed to the red wavelength or whatever like that. All right, so later the boat is floating down the river with the water current heading for town. The river has a width of 60 and a constant depth and flows at a speed of 5 kilometers per hour. Ew, non-standard units. Partway to the town, the river narrows to a width of 30 and the depth remains the same. Okay, so let's draw a picture because it'll make it so much easier for us to visualize here. We've got the wide river of some depth here. Let's just assume it's rectangular just to make it easy. It has a width of 60 and a depth and a constant depth, and it flows so we don't care about the depth. And it flows at a rate of 5 kilometers per hour. Now, as the river goes, it's going to become more narrow. It's going to have a constant depth still because I don't want you to have to mess with that. And it's going to have a width of 30 meters. Well, what's it going to be? Well, it's got, if you're using the formula, A1 times V1 is equal to A2 times V2. You got half the area, it's going to have twice the speed, right? Because you got to have the same volume of water flowing through the area. So calculate the speed in the narrow section. Well, the V is going to equal 10 kilometers per hour. That's all you got to do for that. Okay, not too bad. Looking at this one here. So we'll look at the question in a second. We've got to read this picture first. Question 1 and 4, blah, 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 blah. Okay, show your work for each space provided after the part. Okay, so we didn't need this slide. Oh, well. So here's what we do. We got a faucet. It's got some measurements that are all over there. It's got an A and a B. Let's do it. So 2 students observe water flowing from left to right through a section of pipe. Okay, so one thing we know is water is going this way, which decrease in diameter and increase in elevation. The pipe ends on the right where the water exits vertically. At point A, the water is known to have a speed of 0.5 meters per second and a pressure of 2 times 10 to the 5. So P equals 2 times 10 to the 5. The density of water is 1,000. Okay. Nice. Easy. The students disagree. What else do students are quite disagreeable about what the water pressure and speed at point B. They make the following claim. Student Y claims the pressure at point B is greater than point A because the water is moving faster. Student Z claims that speed of the water is less at point B than at point A by the conservation of energy. Some of the water's kinetic energy has to be converted to potential energy of the Earth system. Yes, okay. So there's something right in both of them. Of course, that's how it typically plays out. So indicate student Y. What is right about student Y? Color Yee. All right. The pressure is greater because their water is moving faster. Well, is the pressure greater? Maybe. Maybe not. We could figure it out. But I suppose we could. But what we do know is that the water will be moving faster. Ooh, do we? Let's find out. Let's do some math before we jump into it here. So we have a beautiful formula. Hashtag Bernoulli life. So P, where'd it go on here? Plus rho times GY plus 1/2 rho V squared. Okay, so there's our formula, and there's two halves to this. This side we'll call A, and this side we'll call B, but they're going to look the same. P plus rho GY plus 1/2 rho V squared. All right, so we know a lot of these things here. Okay, so we know the difference we know everything about part A. So let's plug that in. So we're going to have 2 times 10 to the 5 plus rho, which is 1,000 times 9.8 times y. We'll just call this our 0 level here. So we don't need this one anymore. Times 0 plus v, so 1/2 1,000 times v squared, so 0.5 squared is equal to p. So now we're worried about point B here, okay? So we figured out everything that matters for part A. So we know the height's right there. But what is going to be the speed? Well, water is incompressible, okay? So we have to figure out what the difference is. We have to do the flow rate here. So we're going to figure out everything, and then we can confirm. All right, so flow rate, we have A times V is equal to A times V, just like we had in the previous problem here. Now on the left-hand side, we'll do position A. Position A is going to be pi times 1.25 squared, all right, because I gave you the diameter because I like to make things difficult, times 0.5 is equal to, what's the width up there? The width is going to be pi times 0.75 squared times v. All right, the pi's can cancel out because yucky. All right, so now we got to do a little bit of math here. 1.25 and 0.75 squared times 0.5. So I'm getting a velocity of 1.3888. I'm going to go 1.4 meters per second. All right, so I know what that speed is. I can plug it into here and we can find out what the big P is. Plus 1,000 times 9.8 times y, which is 5, plus 1.1/2 times 1,000 times 1.4 squared. All right, doing some math here. So the math is going to give us a P is equal to 150,145. All right, so that's going to be a 1.5 times 10 to the 5 pascals. All right, so now let's go into this here. So student Y claimed the pressure is greater. They are wrong. That is not true. But they say because the water is moving faster. Any aspects that they're right, the water is faster. But it's the pressure is not higher. Water is faster. It's faster because the area went down. Indicate which aspects of Y's claim are incorrect. The pressure decreases. Decreases because the speed goes up and the height goes up. That'll cause the pressure to go down because there has to be a conservation right here, right? When this goes up and this goes up, the pressure has to go down. Pressure decreases since V and H increase. You should use words when you're writing here, but I can explain it to you. Okay, now let's look at student Z. Indicate any aspects that are correct. Speed of the water is less. Well, that's not true. Because the water's kinetic energy is converted to potential energy. Well, yes, there is potential energy. Potential energy increased. All right, because it went up. Ta-da, definitely. Indicate any that are incorrect. Well, they're incorrect because the speed is more. The water is faster. The water is faster because the area decreased, so the speed is going to increase, right? Because the flow rate has to stay the same. Ta-da. Okay, there's a second half to this guy now. So calculate the following, blah, blah, blah. Speed of the water in the pipe. We just did that. The pressure in the pipe. We just did that. I can't go back to it. So, we did that a little while ago. Okay. The valve to the left now closes off that end of the pipe. A section of the pipe shown is still full of water. The water is no longer flowing. Okay, so we're closed off there. Calculate the absolute pressure at point A. The pressure that indicates the height of the atmosphere. Okay, so absolute pressure, we have a formula for this. Okay, so P is equal to P0 plus rho GH, right? The absolute pressure is going to equal the pressure of the atmosphere, so that's the 101,300, right? It's on your formula sheet as a constant. Plus the density is 1,000 times gravity, which is 9.8, times H. How below is it? It is going to be 6 below because the point B is a meter below the surface there. All right, and that's it. So all we got to do is type this in now. So 101,300 plus 1,000 times 9.8 times 6. So at the end, you're going to get a P is equal to 16,0100 pascals. All right, easy. An air bubble forms at point A. Nice. On the figure below, where the dot represents the air bubble, draw a free body diagram showing and labeling forces, not components, exerted on the bubble. Draw the relative lengths of the vectors to reflect the relative magnitudes. Okay, so you have air. What's going to happen? The biggest thing right here is going to be your force of buoyancy. Now, it does have mass because air does have some mass to it, so you're going to have some mg, force of gravity. But it's going to be way smaller than the force of buoyancy because it's like 1,000 times more dense the water is. So it's going to be a lot smaller here. And that's it. That's all it wanted, right? Draw a free body diagram showing labeling forces. There's no left or right forces there because there's no water flow at all. All right, so that's it. Hopefully that flowed well. All right, keep the pressure up. Have fun. We'll see you on the next one if you fill out that poll to know what you want to review. See ya.